Hello, everyone. Good day, good afternoon. This is webinar number 13, AM Smart. We are still continuing on the webinar on advanced manufacturing of smart materials and structures. And thank you for joining us today with two prestigious speakers that we have. I leave the introduction to the host of this meeting. The host of this meeting is Professor Ian Gibson, Director of Fraunhofer Center, Advanced Manufacturing Center, University of Twente, and also he's a professor in Department of Design, Production, and Management at University of Twente. So we are going to have like half two speakers for this meeting, and the topic of the presentation and everything will be explained later by Ian. Okay, Ian, floor is yours. Please go ahead.
Okay, well, thank you very much, Murshad, for the introduction. It's very nice to have a couple of really good speakers here today. And the first one I will introduce, which is Professor Mohammad Elahinia from the University of Toledo in the US. Just to maybe mention briefly before I hand it over to Prof. Elahinia, is to say he's I think currently attending a meeting and taking a little bit of time out to present this this talk to us. So we're very grateful to you for doing that. Secondly, therefore, we can maybe excuse that there may be a little bit of background noise from you during your presentation. Hopefully, it won't get too much in the way. The presentation is going to be about functionally graded nickel titanium alloys. And we're going to be directed from simulation-driven design to experimental validation for elastocaloric and biomedical applications. So without further ado, I'll ask Professor Elahinia to start your presentation.
Good afternoon and good morning, everyone. And thank you, Professor Gibson, Professor Mahpouya, for the invitation. And it's a great pleasure to be presenting with Professor Oliveira in the same session. My apologies if you hear some background noise. In the room next to me, I'm in Baton Rouge, Louisiana. There is a conference going on, so I'll try to speak louder to suppress the noise. What I'm hoping to present today is mainly focused on the advantages that additive manufacturing through functionally graded structures can bring into elastocaloric cooling. Just as a way of appreciation, the work has been done by the members of my group. And if you've visited, you've seen this building. If not, I hope that you visit in near future. We are located in Toledo, Ohio, in the northern central part of the United States, by Lake Erie. This is this lake and the collection of 4 others are the greatest, largest freshwater resource in the country. The trend that we see, and incidentally the meeting I'm attending, is that there is a growing demand in general for energy, but more specifically when it comes to cooling. The demand for cooling devices are on the rise, and they're becoming, fortunately, more accessible for developing countries, which then puts a pressure on the environmental aspects of current cooling devices. The current material that enables cooling are super pollutants. They're highly toxic. These are the conventional refrigerants that are being used, and even in the next generation of refrigerants, these issues exist. And just to put it in perspective, the estimate is roughly 20% of global electricity consumption is for cooling, to put this in perspective for all of us. And there are some movements on replacing the hydrofluorocarbon type materials. There is the Montreal Protocol and the Kigali Amendment that phases out these materials over time. Of course, the CFC, which was the most, the traditional material, has already been phased out. So if you have a cooling system that has CFC in it and it needs recharging, most repair people would not recharge it. You have to actually change the system. And then the next generations have been on the market, and there are potential of using propane or butane as solutions. They're not as pollutant, but they're highly flammable. They're fuel material, actually. And there has been use of ammonia and CO2, but they have their own challenges. So the technology that stands out is a non-vapor-based, non-liquid-based solution, which relies on solid-state phase transformation in material by applying a force to cause the temperature change. And the generic name is elastocaloric. And in a system like that, there is no liquid, no risk of leakage. Therefore, the material is generally environmental friendly. So in the cycle of producing the material and recycling the material, the expectation is that there is no significant environmental aspect, and many of the features that prohibit and limits the use of current technology is not there. No flammability, and also very high efficiency when it comes to the material performance. And the other side is the temperature range is quite large, so the limitations on temperature ranges also can be elevated with this technology. The essence of elastocaloric is, as I said, through a phase transformation from a parent austenite to martensite. What you see here is a stress strain curve of the material. As we load the material from the parent phase to martensite, there is heat release, and when it unloads, the heat gets absorbed. And this is the latent heat associated with thermodynamic state of the material. And this has been studied extensively, and has a variety of prototypes have been made. So one of the earliest attempts has been using wire-based devices. Wire is the most widely available geometry when it comes to the most famous alloy that has this property, nickel titanium, or NiTi or nitinol. This is the easiest, most accessible device, a geometry rather, that has been the basis of using in this, for example, in this geometry. So what you see here is there are two discs that are parallel to each other. There is a central axle that causes rotation, but one of the two discs is slightly either tilted, or there is a cam device attached. The yellow face that you see is the cam device. And as these wheels travel on the cam device, the distance between the two discs and the length of the wire changes. So this is exactly what I showed you on the previous slide. So the material that is the elastocaloric material goes through loading and unloading. So as it goes through this larger length, it gets loaded and it releases heat. And when it comes back to the other side, which is the shortest length, it gets unloaded and absorbs heat. And the way to cause cooling is by directing the heat away from the system and directing the cooling capacity to the area that needs to be cooled. So in one iteration, the German group led by Professor Selecki created a can cooling device that was presented as SMST in Portugal, and later they have kept working on the variety of applications. There is also an effort in using other geometries such as tubes, and also attempt at increasing energy efficiency of these systems. As you see, there is loading and unloading that needs to happen. So in this structure that you see at the bottom, two of these devices are put into an antagonistic format. So as you load one, the other one gets unloaded. So you gain improved mechanical efficiency. And there are a number of ways that you can run these systems. In one mode, the system is continuously run, and the fluid continuously flushes over and changes direction, and in a regenerative type application. Which is shown here in the regenerative application. There are 2 heat exchangers and 4 main valves involved, and essentially the same fluid flows over the device and exchanges higher and lower temperature. And because of this mode of operation, there would be a temperature gradient formed on the device. So in other words, either the top portion or the portion that is closest to the hot heat exchangers will be operating at the higher temperature than the rest of the structure. And that's the motivation for the work that I'll be focusing on using additive manufacturing to improve efficiency of elastocaloric devices that are being used in a regenerative architecture, which naturally tends to a distribution of temperature on the device as this device reaches a steady state and in operation. And what you see here, so that's the topic, I'll get to it, but just to give you a more perspective of the variety of devices that are possible, you see a variety of ways of bundling the elastocaloric elements to improve heating and cooling capacity by putting many devices in parallel, and this way increasing the capacity. So with that out of the way, this image actually shows the heat gradient, the temperature gradient rather, that happens. This is a bundle of tubes. It shows the loading and unloading and heating and cooling, but because of the mode of operation, the entire device is not in a single temperature. And what I need to add is that the performance of elastocaloric materials is temperature dependent. So as the temperature goes up, which as you can see on the slide on the right, this hysteretic plot that shows the loading and unloading actually shifts. In other words, in order to cause the solid state phase transformation, if you're operating at a higher temperature, you need to exert more stress. So that's what this plot, labeled as B, shows. So in other words, if the material for the entire elastocaloric device is made of the same alloy, which essentially means it has the same transformation temperature, and yet you operate it in this mode, either you are going to overstress part of the material and cause permanent damage, or you are underutilizing another portion of the device if you're setting your application in a way not to exceed maximum allowable stress. So the question is how we can address this issue and take full advantage of the elastocaloric capacity of a device and therefore increase efficiency. So this is more of a question of efficiency, because if you limit your stress in order not to damage the material, you are underutilizing portions of the device and essentially leaving unused phase transformation on the table. And there has been multiple attempts at addressing this issue. I'm showing a few of them, but the people have mostly looked at using multiple materials with different modes, different phase transformation temperatures. So addressing the issue by shifting the transformation temperature upward for the area that is operating at higher temperature, and shifting transformation temperatures lower for the areas where the material is operating in the colder temperature. So how could you practically achieve that? You can look at this lower side. Imagine that each bundle of these tubes, there are 4 sets of them, have a different phase transformation temperature. So this way you can get closer to a uniform stress, strain, and phase transformation behavior, because the colder part, it is actually also is a material that has lower phase transformation temperatures, so you can get close to uniform stress, strain behavior. The other possibility is to create bundle of material and put them this way, instead of being in series, being in parallel, and essentially looking to achieve the same improved efficiency. So these are 2 of the attempts. What we try to bring to the table is another way, and that way is fabricating these elastocaloric elements through printing additive manufacturing, which brings its own complexities and issues, but then also it provides ways of addressing that specific issue that I mentioned, the issue that an elastocaloric element would be in a range of temperatures and require a change in the material. Just as an overview, in our lab, we have so far tried 3 different additive manufacturing techniques for manufacturing phase-changing material, also used for elastocaloric application, a powder laser-based system, a wire-based DED system, and more recently, a binder jetting system. And we have, of course, done characterization on the functional properties, phase transformation properties, as well as the structural properties of these alloys. So just you have seen that there is an effect on, as you change the parameters of fabrication, you can affect density of the material, but you can also affect the microstructure of material, and ideally get closer to behaviors that would be applicable and desirable in your application. So there is, as you change, for example, in laser powder bed fusion system, as you change the power of the laser or effective power that you deliver to the powder, you have that ability to change the behavior. So this is an earlier work that we published in 2019 that showed it is possible to create superelasticity in parts that are fabricated in the device and get a stable behavior, which is the essence for elastocaloric behavior. We also showed that in the same part, it is possible to create different stress strain profile, which shows different style of phase transformation. We have, like others, also looked at other ways of affecting properties, such as the relative direction of printing versus the orientation of the part, and have shown the effect of it. One of the earliest tests that we did for elastocaloric was not really attempted to be an elastocaloric device. This was a biomedical device that we had fabricated. But when we did mechanical testing, we were doing thermal imaging, and we showed the effective heating and cooling of the device. But then we started more intentionally looking at fabricating parts for elastocaloric behavior. And we also looked at the effect of various parameters, including direction of printing on elastocaloric behavior. One question that we tried to answer early on is it possible to create a functionally graded part in one piece? Is it possible to print a structure with two distinct behavior? And this is an attempt of achieving that. So we have a part that is half in room temperature, half superelastic and half shape memory. So the top part, when you load and unload it, goes through stress recovery, but the bottom part, in order to go strain recovery, it has to be heated up. So that was a promising result, where we attempt now to build on and relate to elastocaloric devices. So by that, we extended the block fabrication to a tube fabrication. And our answer to that, the challenge that I mentioned, is to print parts that have multiple, in each section, we have a different transformation temperature. And based on what I showed you, in principle, is possible. And there is this is a patent pending invention and methodology to create a tube with multiple transformation temperature. But this may be more challenging than the other way of addressing that issue. And that other way is, if I move this out of the way, the other way of addressing this issue is to work with geometry. In other words, you can effectively adjust the level of stress that the material sees instead of going through the more complex route of trying to create a functional graded by adjusting the transformation temperature. And these parts have been fabricated in our lab, and our students are actively working on characterization and showing the benefits of it in elastocaloric performance. But regardless of the method, either with the geometry or with having a series of transformation temperatures, what we attempt to do is shown in this Clausius-Clapeyron plot. The plot shows the challenge that I showed you. As you change the temperature in order to achieve the same transformation in the material, you have to increase the stress. But with this, we are effectively climbing down that staircase in each of these steps that we create in this functionally graded device. And the plan is for this to be tested in a setup similar to this. For that, we are working with colleagues, Dr. Tushek at Ljubljana University, to test the material, and we're hoping to get there within the next few months. But before getting there, we did some calculations based on simulations to show that when a device like this is used versus a regular device with a single transformation temperature, we are able to achieve better efficiency, more cooling capacity, and these are published by one of our PhD students who has graduated. We also attempted to bring the data we collected to a machine learning platform, so we can use it for design purposes of the next generation. So we trained a neural network model with the series of experimentations that we have done and others have done. So as you know, NASA a couple of years ago released a huge database that is mostly conventional fabrication, but it also has some additive manufacturing data points that we have used to train this in order to use it more in reverse of what are the ways of achieving a variety of transformation temperature in one build. And we created some heat map to show the effects. So on this one, you can see the power versus velocity and the areas that would be viable in fabrication. So that's in conjunction with the model that I showed you. So the other area, I want to be respectful of everybody's time. Let me do a quick time check. And Meshad, is it good? Are we good with time? Should I pause at this and transition to the next one, next speaker?
Yes, that would be
Okay.
great because
Okay,
we
we can
already
share these slides
yes.
and stop at this point. Thank you again for the opportunity. It was a pleasure to see you online, and hopefully looking forward to see you in person in the fall.
Yeah. Thank you very much also for your presentation.
Yes, indeed. Thank you very much, Prof. Elahinia. I believe that you need to now go back to your meeting. So unfortunately, we cannot accept questions directly from you, but I do believe that you have a colleague, Dr. Shiva, who may be able to answer. Is that correct?
They're here, yes. Two of our students are in the audience, and they will do their best to answer questions if there are any.
Okay, it's a good test for them, huh? Okay,
Yes.
So what we will do, I think, is we'll leave the questions until the end of the overall webinar, i.e., after the next speaker.